Chapter 13, the costs of production. Things we'll cover this chapter. What is the production function? We'll look at the production function in three different ways: a table, a graph, and then a diagram that I'm going to introduce you to. We'll define marginal product and how it's related to the production function. But looking at this title here, this vocabulary, marginal product, you should kind of already be able to get a feel for the definition. Marginal, right? We already know that this means additional or incremental. So the additional product, in other words, the additional output. In particular, what is the additional, what is it? It's the additional output from additional input. We'll define that a little more explicitly in a bit. We'll talk about a bunch of different types of costs and their properties, and we'll also explain how they relate to output, to each other, and to output as well. Remember, the title of this chapter is The Costs of Production. So we will be relating costs to production. We'll talk about the difference between the short run and the long run. In fact, I'll talk about it right now. Later on, I'll talk about it a bit as well. But after I talk about it now, you should know the definition or the distinction between the two. The short run is a period of time in which at least one of the inputs into the production process is fixed. So it's not defined by the short run nor the long run. They're not defined by time. They're actually defined by a characteristic, a property of production. So if one input, at least one input, it could be more, but if at least one input is fixed, then we say that the firm is in the short run. The moment all inputs into the production process are variable, meaning you can change everything, then the firm is said to be in the long run. So again, the long run means the firm can change all inputs. It can change its labor, it can change its buildings, it can change the land that it's on. Everything is variable. That's the long run. If there's one thing that's fixed, typically it tends to be capital, like the size of the building, the number of machines it has. If there's one input that's fixed, then the firm is said to be in the short run. We'll come back to that in a bit. And then we'll end with what is known as economies of scale. This is actually a long run phenomenon. So according to what we just said, or what I just said, that means that all inputs are variable. So economies of scale is something we talk about when the firm is in the long run. That means it can change everything or anything. And whenever you hear the word scale, think about size. So economies of size, of changing the size of the firm. Doubling its size, like doubling labor, doubling the square footage of the building, doubling the machines, or tripling it or halving it. That's what we mean by scale, changing the size of the firm. We'll get back to that. Actually, we'll cover that at the end of this chapter. And this particular concept does tend to separate my A students from my B students and from my C students. This chapter in general is pretty challenging for students, in particular this last part, but also the second bullet point, when we start talking about the different types of costs and their properties. I actually like this chapter a lot, but it does get pretty dense rather quickly here. All right, so let's talk about some assumptions we're going to make. We're going to assume that the firm's objective is to maximize profit. So that will be our working assumption. That's actually a very realistic assumption, even though you may say, well, actually that firm is a nonprofit. An economist would say, really, a nonprofit? Right? We know that profit is the difference between revenue and costs, or total revenue and total costs, technically. And even a nonprofit wants to make its costs as low as possible and wants to make the money coming in, the revenue, as high as possible, and the difference between the two as big as possible. In other words, even a nonprofit has this as a working objective. They may not say that, but they are actively trying to minimize their costs and actively trying to bring in as much money as possible. So this is a very realistic assumption. We're going to assume once again that firms are trying to maximize their profit. So again, this will be our working assumption. Let's briefly talk about the difference between explicit and implicit costs. You are in an economics class. Remember, the true cost of something is what is given up to get it, right? The true cost is what we call the opportunity cost. And in an economics class, we don't care if you actually paid money for a cost or not, right? So for example, the cost of sitting through this lecture right now, you're not paying money. You already paid that. right? But to sit through this lecture for another hour or however long it is, you're not paying cash money for this particular time of yours, but you are giving something up, right? You'd maybe be watching a show instead, or maybe working instead, or maybe being with your kids, or washing clothes, or sleeping. Who knows what else you would be doing, but you are giving something else up. And that, as you know, we call that the opportunity cost. Opportunity cost is anything that's given up to get something, whether it's in dollar amount or if it's in like the value of your time. And so this is where we get into the distinction between explicit costs and implicit costs. Explicit costs involve a payment, some outlay of money. So wages, for example, or if, I charged you to sit through this lecture, I said, hey, $10 to sit through this lecture. That would be an explicit cost. Of course, on top of that, we can also add the next most valuable thing that you'd be doing with your time. And that type of thing, right? Like if instead you'd be surfing for an hour, whatever you value that hour of surfing at, that would be an implicit cost. So an implicit cost does not involve an outlay of cash or money, any sort of payment. Okay, so opportunity cost of your time, for example. So total opportunity cost is not just implicit, but it's both implicit and explicit. Okay, I want to make that clear that opportunity cost is not just implicit. People confuse that. So if I charged you $10 for this lecture, and in addition, that means you're giving up an hour of work, then it'd be the $10 plus that value of that hour of work, right? Anyway, so explicit and implicit costs, it's important to know the difference between the two. And so since you're in an economics class, we're going to make a distinction between accounting profit and economic profit. Accounting profit, they only count those costs that involve a payment. Okay, so it's revenue, money coming in, minus explicit costs. Economic profit is revenue minus total costs, meaning both explicit and implicit. Whenever you hear me or any other economist or in any other econ class that you're in talk about costs, we mean both explicit and implicit. In other words, we mean the true opportunity cost. Okay, so it is possible that a firm is in the positive for accounting profit, but when you actually take into account economic profit, that they're actually in the negative. And you might even see in your lifetime at some point, actually it does happen quite often, where a firm will go out of business even though their financial statements are in accounting profit. Even though their financial statements state that they are in the positive, they actually end up shutting their doors and leaving. Why? Because when they take into account the true cost, the opportunity cost, it's not worth it for them, which leads us to believe that it must be the case that their economic profit is actually negative. So that is possible. Okay. And so, of course, we're going to assume from now on, anytime we say costs or anytime we say profit, we're talking about true opportunity costs, both explicit and implicit, and therefore we are talking about economic profit in this class. Okay, the production function. So the production function shows us the relationship between inputs and outputs. Okay, the production function. Again, shows us the relationship between inputs and outputs. So for the production function, think about a function in your math classes, right? What did you learn about when you learned about functions? You learned that there was an input, in goes x, and then out comes f of x, right? So for an input, you put something in and out comes an output. That's basically how I like to model the production function. So when I said there was a diagram to convey the production function, this is it. And so just imagine that there's this magical black box, which we'll call the production function. And into the production function, what goes into it? We have inputs going in. So, for example, if you're making a table, you have wood and a saw and maybe some nails, right? And a lathe and a carpenter, some labor hours, and then out come the tables, right? So in go the inputs and out come the outputs. This is fundamentally what we mean by a production function. I'm not here to teach you how to make the table, what goes on inside of it, right? This magical black box, right? Or, how to build a bridge. That's what you learn in your engineering classes. I'm just here to describe the relationship between inputs and outputs and ultimately map costs and production. Initially, it's going to seem like, what in the world? She's not talking about costs at all. All she's talking about is production. But you're going to see that this actually maps it provides a way for us to map costs to production. And so another way we can describe the production function is with a table. So for example, let's say that, let's see, how should I describe this? Actually, let's go to the slides. Let's use the example on the slides. So let's assume that we are growing wheat. Okay, so you are Farmer Jack, you're growing wheat, and you have 5 acres of land, and that's all you have. So this is what is fixed. Okay, so you have a fixed amount of natural resources, 5 acres of land. And so by now you should be able to identify that you're in the short run. Okay, and you have a variable input. Your variable input is the amount of workers that you employ. And so what we're going to have here is, again, we're going to depict the production function using a table and then using a graph, basically mapping the table onto the graph. And so we're going to have number of workers, bushels of wheat over here. So L is your labor, Q is your output, right, where you're producing, also known as product. So output and product are synonyms for each other. And so here's our table. And notice that we have output as a function of the input. Right, so we have output Q. So if you're drawing this, which I hope you are by hand, I would put Q here. I wouldn't worry too much about the numbers, but I would put Q here, output, and over here is input, L, okay, our variable input. And so let's say that you don't employ any workers. Well, to harvest wheat, you need to employ some workers. So if you don't employ any workers, yeah, you may have this land, but you won't harvest any wheat. So your production would be 0 in that case, your output, again, also known as product. And when you employ one worker, your output is now 1,000 bushels of wheat. Okay, so we're going to plot these points each of these times. And then if you employ a second worker, your output increases to 1,800 units. If you employ a third worker, your output increases to 2,400 units. If you employ 4 workers, you are producing a total of 2,800 units. And 5 workers, you are producing a total of 3,000 units. So again, output as a function of input. And if we connect these dots, that right there is our production function. Again, conveyed on a table here, but also in this graph where we have output as a function of your variable input. Okay? And so this is a production function. Look at how it looks. Okay? And we actually learn a little bit more by looking at the slope of the production function. We learn a little bit more about the properties of production here. So let's go back to the whiteboard. Let's draw the production function here. Actually, I shouldn't be putting Q there. Okay, actually Q should go over here. Right? Remember, this is output. Q as a function of input. In our case, it's labor. And our production function looked like this. Right, so if we employed no labor, we would produce nothing. And then as we were employing more and more inputs, labor, we would be producing more. Okay. I want to point something out. I want to point out that as we add more input, that output does increase, but it increases at a diminishing rate. Right, so remember, this is our production function. Actually, let me go ahead and denote that mathematically how you would see this. If you take a higher level econ class, you move away from drawing things and we only focus on the mathematics behind it because it's a lot easier to convey these concepts in mathematics. So I do want you to understand that this is a function, right? So let's show you how we would write this. We would say output is a function in this case of the acreage of land, the acres, and then of labor. Right? And the acres of land are, if I knew how to spell, I don't even think I spelled that right. The acres of land are, or did I? Yeah, I did spell it right because otherwise it's acres. Oh, English, my favorite subject. Anyway, so we have output as a function of the acreage and the labor. Right, so in this case, we're holding the acres fixed. So I'm just going to put a bar up here to remind us that it's fixed. And quite often, like I said before, what's usually fixed is not necessarily natural resources. It can be that, that's also fixed. But it's usually what we hold fixed is we say capital. So quite often you might see a production function that looks like this, where we say output is a function, so there's output, a function of capital and labor, right? And so we might put a little bar there on top of capital, not because we're talking about average capital, because you know how sometimes the bar means average. In this case, we mean fixed, okay? So we would say capital is fixed at 100 machines, or whatever the example is telling us. And then a type of function you might see, which you don't need to worry about for this class, but I want you to understand that if you do take the next level econ class, that you will start seeing functional forms instead of having to just draw them. Or in fact, you won't be drawing much of anything. You'll just be working with math. And so a lot of you are business majors, most of you in fact, and then there's some of you that are econ majors. You will definitely, if you transfer, or if you're already at a UC or at a CSU or at some other university, you will definitely have to take the next level class in order to get your degree. At least chances are. Maybe some private institutions won't require it, but most CSU, actually all CSUs and UC systems, if you're in a business program or an econ program, they require you to take the next level micro course. And so I'm just kind of preparing you for that. And I also want you to take this, I guess, this message of me focusing on the importance of making sure you understand what's happening in your like business calc class or your regular calc class, because you're learning about derivatives there, right? You're learning about the linear approximation of curves, and you're taking derivatives, and you're going to be doing that a lot in the next level micro class, looking at functional forms and taking the rate of change of them. That may not make a lot of sense right now, but all I want to say is make sure you take those classes seriously, that math class, because it will prepare you to do well in the econ class. And so you'll see something like output is a function of, k to the 1/2 L to the 1/2. So it's again a function, output is a function of capital and labor, and we're just raising it to these powers. So that's how you would see it in the next level micro class. In this class, we're not going to worry about it. We're just going to say, let's just draw it or use a table. Okay. So this is our production function. I'm just going to erase this here to keep it clean. There we go. And I want you to notice what's happening to the slope. Okay. And so let's pretend we're adding an additional amount of input, a marginal amount. So we're going from no labor to a marginal amount of labor. We're changing labor by this much, right? So we would say that this is delta L, the change in labor. When we do that, when we add this much labor, whether it's 1 unit or 1 worker or 10 hours, whatever it is, we're going to fix it every time we add an additional marginal amount of labor. So however many it is, in this example, let's pretend it's 1 worker. What does it do to output? We go from nothing to this much more output, right? So here's our change in output. So again, change in input, change in output, right? So that's the additional output. That vertical red line is the additional output we get from that additional input. Let's do it again. Let's add the same marginal amount of labor. I want it to be the same. I don't want it to be too much, because then the output isn't comparable. I also don't want it to be too little, because then also the output is not comparable. So we want to make sure that at the margin it's the same comparable amount. So I want to make sure that that arrow is basically about the same size. So here's my additional labor. Again, this is the same delta L. And from that marginal amount of labor, not from this amount of labor, from this additional amount of labor, this is how much more output we're getting. That's our change in output, right? So our change in output as we change input by this marginal amount, delta Q, delta L. Let's do it again. First of all, actually, before we do, notice that how much we're getting at the margin is shrinking. Let's do it one more time, or a few more times. Increase labor. There's my delta L. And you can barely tell right here, but it is smaller than this other one, right? This one was that big. This one's just a tiny bit smaller. So the additional output from my additional input is shrinking. Let's do it again. There's my additional output. I'll show it in green. From my marginal amount of labor. So these green arrows are getting smaller and smaller and smaller. My additional output from this additional comparable amount of input, delta L, is shrinking, right? So as we're increasing labor, right, output is going up, but it's going up at a decreasing rate. So it's increasing, but it's increasing by smaller and smaller amounts, right? So output is increasing, but at a decreasing rate. In other words, the slope is getting flatter, right? And the slope of anything, as we know by now, is the rise over the run. You know that already. And in our case here, well, what's the rise? Our rise is delta Q. That's our rise, right? How much? Here's our rise right there when we added that additional amount of labor. And here's our run right here, right? So delta Q over delta L. Look at what this says mathematically. The change in output as we change input. The rate of change of production, right, of product. The rate of change of product as you change your input. This is what is known as marginal product. In particular, the marginal product of labor, because it's labor that we're varying. So we're saying marginal product is the change in output as we change input. Marginal product. Listen to those words. Marginal product. Additional product. Additional product from what? From additional input. The marginal product of labor. The textbook, I think, uses MPL with a capital L. I don't like that. Most textbooks and most websites use a subscript L. But whatever floats your boat. Okay. And so marginal product is the additional output from the additional input that we use. In other words, it is the slope of the production function. It is the rate of change of the production function. Let's redraw this production function right here. So here's output as a function of input. Notice that the marginal product, the slope, right? Slope of the production function. The slope of the production function is getting flatter, right? Here's that steep, then that steep, then that steep, and then that steep, right? It's getting flatter. So as we're adding more labor, the marginal product of labor is decreasing. That should make sense according to the plot we just drew. As we add more labor, let's look at this. As we add more labor, I'll use blue. As we add this initial marginal amount of labor, there's our output. When we add another marginal amount, our output, our additional product, our marginal product is shrinking. Here's more labor, the additional output is shrinking. Here's more labor, the additional output we get from that same size of labor, the additional output is shrinking. Right? So marginal product is going down. As we increase labor, the production function is increasing, right? But it's increasing at a diminishing rate. And so that's why we have this production function that is curved, like this rather than like this. Okay? And so this right here, this concept, is what we call diminishing returns. Diminishing returns. The returns to labor, what do you get from labor? You get output, right? The returns to your studying, what do you get? Grades, right? The returns to your hours of work, for you, it's your wage, right? So the returns to labor here are diminishing. Sure, it's going up, but each additional labor hour is giving you, or worker, if you're looking at workers versus worker hours, is giving you less and less at the margin. So we have what is known as diminishing returns, also known as diminishing marginal product. Okay, diminishing marginal product of labor in particular. This property will always eventually kick in. Always, 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 always. Will always eventually kick in. Initially, you can have increasing returns, and I'll show you an example of that in a second, but diminishing returns will always kick in. Think about it. You're a farmer, you only have so many acres, or forget farming. Let's say you're making, I don't know, sandwiches. And look at the room you're in right now. Okay. Let's say you keep on adding sandwich makers, workers, labor. You keep on adding workers into that room that you're in. You keep on adding, and you keep on adding, and you keep on adding, and you keep on adding. At some point, you're going to add so many people into that room that we're going to start bumping elbows, right? We're going to start getting in each other's way. Think about it. Like right now, like pretend you're like a sardine all squeezed in, all right? Or kind of move your elbows and you're hitting somebody else. As you add more and more of your variable input, at some point you will start, this variable input will kind of start bumping elbows, whatever the variable input is, but it's good to think about labor. We'll start bumping elbows, right? Why? Because there's a fixed input. As long as something is fixed, eventually, you will always eventually kick into diminishing returns. There's lots of things that exhibit this property. Production will always eventually exhibit this property. Maybe not initially. Again, I'll give you an example in a second. But will always eventually exhibit diminishing returns. My favorite example of diminishing returns are relationships. It's sad, but it's true. Right? Think about it. Initially, you meet your significant other. You don't know he or she is your significant other just yet. And you meet him or her, and initially you get all these butterflies, and the returns to hanging out with him or her for another hour or another day are like increasing initially, right? And you're like, oh, I want to get to know him or her even more, and then even more butterflies come the next time you hang out with him or her. And then at some point you get married, right? And diminishing returns kick in, right? They do kick in. They will eventually, those butterflies eventually go away, and it could, that satisfaction, or however you want to measure that, eventually it starts diminishing. It could still be going up, but it's increasing at a decreasing rate. By the way, this is also why you don't want economists to be therapists, right? Because, you come to me, I'm like, psychiatrist Ruth Morales. You're like, what should I do? Or psychologist. And I'm like, yeah, it's your diminishing returns. You got to work on that. And honestly, in mathematics, we would say you got to work on getting that steeper, right? Getting your function up like that. So what would you do in terms of economics? We can look at relationships. In fact, some people do study relationship. It's called household economics, or economics of the household. And one way you can do it is maybe compromise, or maybe, take a vacation, or maybe go to therapy, or maybe, give each other a little bit of space. Hey, honey, we don't need to hang out with each other all the time. You go do your thing. You want to go watch the boxing match? Cool, have fun. Or, hey, you want to go, watch opera? Whatever, have fun, do that, enjoy. Right? So again, working on getting this slope steeper, because the slope is that marginal product, right? So you want to get that slope to be steeper. And yes, it's a sick and twisted way of looking at therapy, but therapy can help achieve that. Again, you may not like thinking this way, right, like an economist to describe relationships, but it is realistic. So that was one example. I wanted to give you a little bit more of a concrete example. Let me go back. Let's focus on this one. Right, our marginal product, which is the slope, is getting flatter. Okay, and by the way, this production function, let's draw it again. Output, wheat, as a function of input, labor. Okay, by the way, production functions always output as a function of input. Always, 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 always. Except we're using Q and we're using L. Okay, but it's fundamentally a production function that we're plotting here, so that's something I wanted to emphasize. Also, let's go back to this one, which shows diminishing returns, because again, that slope is getting flatter as you add more labor. And what else did I want to tell you about this? That the production function is also known as the total product curve. So whether you hear production function or total product curve, it means the same thing, right? Just like I had drawn before in the math, I said total product, Q, is a function of your inputs. Right? We just happen to be holding capital fixed or natural resources fixed in our example. So total product curve or production function, same thing. Why did I mention this? Because the slope of any total is always the marginal. Because the marginal is the slope, it's the rate of change. Right? So anytime you're plotting a total and you take the derivative, or you find the slope, mathematically it's the derivative of the function. If you don't know what a derivative is, that's okay. You don't need to worry about it for this class. But basically, the slope of it, right, of a total function is going to be the marginal. Always, 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 always. So if we're plotting a total cost curve, and you look at the slope, then the slope is the marginal cost. Okay, so the slope of any total, whether it's in an econ class or not, the slope is always interpreted as the marginal, the rate of change. Okay, now let me give you an example of when it's possible that it doesn't immediately start diminishing, that we don't immediately have diminishing returns, also known as diminishing marginal product. It can be the case that initially we have increasing returns. So let me give you an example. Let's say we make shoes. Totally made up example. In fact, you're going to see that you don't want to buy my shoes. I make shoes, and let's say I have a fixed space. Think about the room that you're in. Maybe that's my building, my room, my assembly plant. And I employ workers, and we're going to look at how much is being produced. Okay. If I don't employ any workers, by the way, I prefer to look at worker hours rather than workers. So we're going to think of worker hours here. The reason worker hours are preferable is because think about you and me, or you and another student, student A and student B. Student A, we can't compare student A's output in a day compared to student B's output in a day, because what if student B worked 10 hours and student A worked 6 hours? So their output is not comparable. But if we look at 1 hour, student A's 1 hour, student B's 1 hour, then we can compare their output. Or maybe even student A, we're only focusing on student A, and student A is working student A's first hour versus student A's second hour versus student A's third hour. Okay? That's still, those hours are comparable. Actually, this made me think of another example for you guys of diminishing returns kicking in. Right? So for example, it could be studying. Actually, that would be your input. Studying, that affects your knowledge acquisition, how much you learn. Right? And so learning as a function of studying. And you know, that first hour output's pretty big. That second hour, maybe you're a little tired. Eventually you're studying a little too much. Sure, you're still learning, but you know, you stop having as many gains. You're tired, right? You've kicked into diminishing returns, and you know that happens, right? I know how many times have you done that, where you're studying and you study a lot, and at some point your like brain is all mush, and you're like, I can't anymore. My brain hurts, right? You have a headache, or you're tired, and you're not really absorbing material anymore. You have kicked into diminishing returns. I get students come into my office all the time, and especially around finals, they come in and they're all like bloodshot eyes, and they look super exhausted, and they're like, Professor Morales, how can I do better on this exam? I'm like, sleep, honey. You need to sleep, because sleep is part of the production process into getting good grades. All right, so I'm like, you've kicked into diminishing returns. I can tell your physical state is telling me you need some sleep. Right? So to get back into these bigger returns, right, then you need to go sleep and kind of reset. Right? So again, this concept applies to a lot more than just production. Okay, let's go back to my shoemaking example. So if I don't employ anyone, then I'm not going to make any shoes, obviously. Let's say I employ one worker, and this one worker gives me, I don't know, 10 pairs of shoes in an hour. Okay. By the way, let me describe how shoes are made in my factory. Shoes have 3 steps. You cut leather, that's one step. You cut rubber, that's another step. And then the third step is you bind those 2 pieces together. And then again, cut leather, cut rubber, bind those pieces together. Cut leather, cut rubber, bind those pieces together. Or maybe if I have this one worker working for an hour, maybe this one worker cuts leather, cuts leather, cuts leather, cuts leather, and then cuts rubber, cuts rubber, cuts rubber, cuts rubber, and then binds, 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 binds. That could happen too. Okay. But either way, I have this one worker doing all 3 steps. I told you don't want to buy my shoes, right? You wouldn't want my shoes. You don't want me making shoes. I don't know how to make anything except produce econ lectures, honestly. And maybe tacos. I always say this, tacos and salsa. Those are the other 2 things I know how to make. Other than that, you don't want me to make anything for you. Anyway, so we have this one worker working, and this one worker in 1 hour, say, can make us 10 pairs of shoes. And then I think about it, and I'm like, you know what? Actually, this is really 2 steps. It's the cutting of the leather and the rubber. It's cutting, and then binding. So I'm going to employ a second worker working for 1 hour, so 2 worker hours at the same time. And when I do that, my output goes up to, say, 22. Okay. Then I think about it some more, and I'm like, actually, it's not 2 steps, it's 3 steps. It's the cutting of the leather, which is distinct from the cutting of the rubber, which is distinct from the binding of the 2 pieces. So I decide to employ 3 worker hours. And when I do that, maybe my output goes up to, I don't know, totally making this up, 36. Okay. But then after that, if I add another worker working, so I have 4 people working for an hour, so I have 4 worker hours going. If I have this 4th worker hour going, this 4th worker basically has to go help the other ones, and they are now getting into each other's way. Right? When this worker goes and says, hey, let me use the scissors, or hey, let me use the glue, or whatever, you're getting into the way of those resources that are available to those other workers. So since you are helping, it can help increase production, but production isn't going to increase at the same rate anymore because now we have to share the fixed input, like the machines, for example. Let's say the machines in the building are what were fixed. So sure, my output may go up, but it's going to go up at, say, a diminishing rate. Maybe it goes up to, I don't know, let's see if I can add. If I add 13, so let's say this one was 14, let's say this was 13, so let's say it goes up to 49. Okay. And then I add a 5th one, and maybe my output goes up to, I don't know, 60. Okay. And they add a 6 worker hour, and then let's say output goes up to, I don't know, 67. Okay. And notice that if I were to find the marginal product of labor, right, marginal product of labor, remember what that is. It's the change in output when we change input, delta Q over delta L. Well, you can't find the first one because we don't go from negative labor hours to 0, right? So we can't find that one. We don't have a delta L, so we can't do that one. But we can do the next one, right? When we added an hour, our input increased by 10. So our delta Q is 10. Our delta L is 1. Here's my delta Q, output increased by 10. Here's my delta L, input increased by 1. Right? So the marginal product of the first worker hour is 10. The marginal product of the second worker hour, my delta Q is 12. My delta L is 1. So I have 12 divided by 1, it's 12. Right? The additional output from the additional input, what did this third worker hour give me? It gave me 14 units of output at the margin. The 4th one gave me 13 units of output at the margin. The 5th one gave me, again, I added an additional labor hour, it gave me what? 11 units of output at the margin. And then the 6th one, I added a worker hour, output increased, but it increased at a diminishing rate. Okay? And so you'll notice that the marginal product is initially increasing, the marginal product of labor. Initially it's picking up, but eventually it starts to diminish, just as predicted. It will always eventually diminish, but it can initially exhibit increasing marginal product. That is possible, for example, in my shoemaking story. And when this happens, think about what the production function should look like. Okay? The production function, we're saying that the production function is the total product function. And we said that the slope of the production function, in other words, the slope of the total product function, is the marginal product. So this table is telling us that that slope should eventually be getting steeper, but eventually should start flattening out. So if we were to draw this, the corresponding production function, output as a function of input, labor, our variable input, initially it's getting steeper, but eventually it's flattening out. Right? Initially it's getting steeper, but eventually it's flattening out. When we add, let me focus on this. For those first few, there's the first unit of labor, output is increasing at the margin. Delta Q, you'll notice, initially it's increasing at the margin. All right, my delta Q, which is the vertical arrow, is increasing. It's getting bigger. You're getting more and more output per unit of input. But eventually, that effect starts to diminish. Right? My marginal product starts to decrease. All right, so that vertical arrow, as you notice, again, it starts to get smaller. Okay. So here in our particular plot, we see that basically between here and here, we have our increasing marginal product of labor. And then eventually marginal product of labor starts to diminish. Just like we said, eventually it will always kick in, just like relationships. In fact, this is a more accurate description of relationships. Initially, those butterflies are increasing at the margin, but eventually we get married. And so I laugh, but it's so true. Again, sick and twisted and dismal, which is, by the way, one of the many reasons they call economics the dismal science. And I am not someone to shy away from that. Yeah, absolutely. You want to call it dismal because I'm using functions to describe relationships, but do they accurately describe relationships? Yeah, I'm not going to, bullshit around here. I'm not. This is the truth, right? It does describe relationships do operate this way. Relationships are work. Right? So again, we're trying to describe the way things are, whether or not we like the way we're describing it, they are the way they are. Anyway, so you'll notice, if you haven't already noticed, that I have no problem with saying, yeah, it's dismal. Sure, it's a sick and twisted way of looking at human behavior or relationships. But does it help us explain how the world works? Does it help us understand relationships? Yeah, it does. So there's always some usefulness in it, right? I hope that the stuff that you're learning is not just learning for the sake of learning. I mean, although there's value in that, right? But I really do hope that it's, something that's giving us insight into our reality that we're in. All right. Okay. Anyway, back to this. Let me delete this so we can focus on this. So notice that initially that slope is getting steeper, but eventually it's flattening out. Okay. And so this production function, this is another type of production function, right? Versus compared to the previous one just immediately kicked into diminishing returns. So some production processes immediately kick into diminishing returns. Some production processes sometimes have initially increasing, but always eventually decreasing or diminishing returns. Always, always, always. And why? Because something is fixed. In my shoemaking example, the fixed input were the machines that they had available, the scissors, the glue, or whatever, however you bind them together, or even the building space, right? The facility that you're in, right? Eventually, you will start bumping elbows. Always remember that concept. Okay, so I wanted to point that out, that we can have different types of production functions, and also being able to get marginal product from this story here, right? From the relationship between input and output. Another thing I want to point out is that here, let me erase all these arrows. I happen to, in my example, to increase labor by 1. But maybe I didn't. Maybe I increased it by, I don't know, 5. Okay. Well, if this is 5, that means delta L is 5. So instead of putting a 1 here, I would put a 5, and this would have been 2. And if this one went to, I don't know, 8, okay, then my delta L would have been 3, and my delta Q was 12, so this wouldn't have been a 1, it would have been a 3. 12 divided by 3 would have been 4, right? So don't think that delta L always has to be 1. It doesn't have to be 1. I just happen to use 1 because I like 1. Okay, so I wanted to point that out as well. All right, so now you have a good understanding of production functions and marginal product. Remember the title of this chapter, Chapter 13, the costs of production. Have we talked about costs yet? No, we have not talked about costs yet. So we still need to link this to costs. Okay. And so I'm going to use this example again. Let me just rewrite it. In fact, let me just copy these numbers over here. And I'm going to copy these. Okay. So let's find marginal product again. And so marginal product of labor, to give you some practice. Again, the first one we can't find because we don't go from negative labor units to 0. But the marginal product of the first hour gave us 10 units at the margin. The second hour gave us an additional 12. The third hour gave us an additional 14. The fourth hour gave us 13. The fifth hour gave us 11. And the sixth hour gave us 7. Okay. And let's say, for example, that each of these hours costs $10. So the wage is $10 per hour. That looks like a negative. That's supposed to be. So the wage is $10 per hour. Okay. And that's kind of realistic to say that it's the same regardless of the hour because they're just making shoes, right? So they're pretty homogeneous labor units. In other words, the workers are pretty much similar. And let's think about what's happening to costs as we hire an additional worker. As we employ more workers, our output initially we have our marginal product increasing. Initially, right? Marginal productivity is increasing. So that first worker that cost us $10 for that first worker hour gave us 10 units at the margin. The second worker hour is giving us 12 units at the margin. So this second hour, even though it costs us $10, it's as if it were cheaper. Why? Because it gave us more output than that first worker hour. So these 12 units were technically cheaper to produce because they cost us $10 versus these 10 units cost us $10. So the 12 units were cheaper to produce. Yes, $10 still, but $10 for 12 units versus $10 for 10 units. The third unit gave us even more output at the margin. So these are even cheaper to produce. Yes, the hour cost us $10, but it gave us 14 units at the margin compared to 12 and compared to 10. So if you ask, well, what's happening to the additional cost of production? It's basically going down initially. This concept of additional cost is what we call marginal cost. And we've talked about this before. You've learned about it in chapter 1, right? Marginal cost versus marginal benefit. And so marginal cost, let's formally define it here. It's in your textbook and in the slides, but I want you to get an intuitive understanding of it. Folks, it's in the title. Marginal costs. Marginal, additional. Additional what? Additional cost. The additional cost from producing more, right? So it's basically, let me define it here. I'll zoom in. The additional cost from producing an additional amount of output. That says amount. That's an N. The additional cost from producing an additional amount of product, of output. Marginal cost. Additional costs from producing an additional amount of output. That should make sense again. Marginal cost. The additional costs from what? From producing more. Okay. And so, if your marginal product is initially increasing, remember each of these cost you $10, that hour, that hour, that hour. If those are giving you more product at the margin, then that's basically implying that your marginal cost of production is going down. It's getting cheaper and cheaper to produce. These units were cheaper than these units and these units. Or if you want to think of it the other way, we could say these were more expensive to produce than these, because these 10 cost us $10, these 12 cost us $10. So these 12 were cheaper to produce at the margin. Okay. And so when we exhibit increasing marginal product, or when the production function exhibits increasing marginal product, it's the same thing as saying that marginal costs of production are actually going down. It's getting cheaper and cheaper, that's this part, to produce at the margin. Right? The costs at the margin are dropping. Okay? And so whenever we have an increase in marginal productivity, marginal cost is going down. Also, it goes in the other way. If you know that this is happening, then you know that this is happening. If costs are decreasing at the margin, it must be that we're becoming more productive at the margin. That must be the case. These two things are inverses of each other. They go in opposite directions. Okay. So, with that knowledge, once diminishing returns kick in, and remember they will always eventually kick in. If they don't kick in initially, they will always eventually kick in. So they've kicked in here. Marginal product goes down. Well, $10 to produce 13 units, and then $10 for the 5th hour to give us 11 units at the margin, then $10 for the 6th hour to give us even fewer units. Sure, output is increasing, but it's increasing at a diminishing rate, so these units are getting more and more expensive to produce at the margin. So when diminishing returns have kicked in other words, marginal product is diminishing returns have kicked in, then marginal cost is increasing. It's getting more and more expensive to produce at the margin. $10 for these, $10 for these, $10 for these. We only got 7 units here, versus over here we had 13 and 14 and 12, right? Okay, so there's always going to be an inverse relationship between marginal productivity and marginal cost. Now let's actually plot marginal cost. Okay. Marginal cost here, notice what happens. Initially it's decreasing, but eventually it's picking up. And so if I'm going to plot marginal cost, let me give us some more pages to work with here. We won't need that many. So again, initially diminishing marginal cost, and then eventually picking up. If I'm going to plot that, I'm going to plot marginal cost. So I'm going to look at the costs of producing, the costs of production, the title of chapter 13. And if it is the case that we are initially exhibiting increasing marginal product, that means that initially marginal cost is dropping, but eventually we kick into diminishing returns, which means marginal cost will eventually pick up. So let's convey that property here on the graph. Initially, marginal cost is dropping, but eventually it's picking up. I call it the Nike swoosh. Okay, let me draw it again. This is marginal cost. The marginal cost of production. This plot corresponds to this, not to this one. Because for this one, marginal product is immediately dropping, immediately, flatter, right? That means that we've immediately kicked into increasing marginal costs. So the marginal cost curve for this type of production function does not look like the one we drew up there. Notice we're on different dimensions, first of all. A production function is output as a function of input. Okay? When we're plotting costs, we're saying costs as a function of output, the costs of production. So they're on different dimensions here. For this type of production function, marginal cost immediately picks up. So marginal cost could be like this. It could be linear, or maybe it has a little bit of curvature, like that. But what it definitely does not have is this part here, an initial decrease, because we immediately kicked into diminishing returns, which means marginal cost immediately picked up. Okay, so again, it could be linear, like that straight line I just drew, or it could have a little bit of curvature, but what I know it does not have a part where it goes down and then picks up. Okay, it immediately just picks up. Okay, so marginal cost curve associated with this type of production function immediately picks up, but with this type of production function, because marginal productivity is initially increasing, we have increasing returns and then eventually diminishing returns, then our marginal cost function for this type of production looks like this, right? Where initially the slope is dropping here, right? I'm sorry, the value is dropping here, and then it's picking up. Or the slope, if we're going to look at the slope, I need to go to this function here. The slope of my production function is initially getting steeper, which means, again, steeper, let me use blue. Steeper, which means increasing marginal product, and eventually flattening out, which means decreasing marginal product. Okay, and remember, marginal cost is the inverse of that. And so let's go back to this. When this is happening, that means that from here to here, it must be the case if marginal cost is going down, it's getting cheaper to produce at the margin. Here we are producing, okay, and the cost is dropping. Right? It's getting cheaper to produce at the margin. Then that must be because we are more productive at the margin. But eventually, we will always kick into diminishing returns, Why? Which means marginal costs start picking up. Why? Because something is fixed. We start to bump elbows. Okay? And so we say that when you do get this benefit, this decreasing marginal cost, that's beautiful. It's a beautiful thing if you're a producer. When do we get that? It's when we have the benefits of specialization. Specialization. Notice my story of shoemaking. Remember, it was the leather, cutting the rubber, and binding them together? And remember how I was telling the story? I said I hired one worker, had to do all three things. When I had two workers, I had one worker cutting leather and rubber, and then one worker binding. And then I said, actually, it's 3 steps. Let them fully specialize. I'll have one worker cutting, another worker binding. Or sorry, one worker, let me start over. One worker cutting leather. Second worker cutting rubber. Third worker binding. Right? So they fully specialized. It basically removes frictions from the production process. You don't have to, physically go from one machine to the next. That's a friction. Or maybe it's a smooth transition, but, even just like mentally, it's like, okay, I got to remember with this machine, I can cut my finger off, right? So kind of like slow initially just to get going, right? And so that could also take a toll on production, right? So if they fully specialize, it removes a lot of these frictions from the production process, and therefore that's why we have increasing marginal productivity. But eventually we know marginal productivity will diminish, right? So if and when marginal cost curves have this little Nike swoosh, they have this part of it, this part right here, then that is attributed to the benefits of specialization. This is also known as the division of labor. We divvied up, we split up labor so that it could focus on, each labor unit could focus on a particular part of the production process. Cut leather, you cut rubber, you bind. Okay. All right, so this is what the marginal cost curve looks like. Again, sometimes it could look just straight like this or have a little bit of curvature. And this is when it doesn't have benefits of specialization. An example would be the farming example that was provided in the slides. Another example, this is a very realistic example of a production function that doesn't have the benefits of specialization, that basically just kicks into increasing marginal costs, meaning immediately diminishing marginal product, could be making hot dogs. Think about it. You have a hot dog stand. It's not that big. It's probably the size of the desk that you're in front of right now. And if I'm making hot dogs, I can access the meat and the buns and the tomatoes and the onions and the bacon and the mayonnaise. But then another worker comes in and stands next to me. We immediately get in each other's way. I have to reach over him to get the buns. He has to reach over me to get the tomatoes. I have to reach over to get the mayo. We immediately start getting into each other's way. So there are no benefits of specialization there. Okay. That doesn't mean, just because there's benefits of specialization, it does not mean, for example, here. Okay, so first of all, I just wanted to give you an example of when the marginal cost function does not exhibit that little Nike swoosh, my hot dog story. And now, let me go back to this. Just because this hour, the third hour, was the most productive hour, that does not mean that you should only employ 3 workers. Okay? And here's why. Let me give you an example. Remember, each worker hour cost us $10. Let's pretend that these are little Barbie shoes. Totally making it up. Okay? And so that the price of these is actually, you can sell your good for $1 a unit. Okay? And again, totally made up. Not realistic. A pair of shoes does not cost $1, but who cares? When that first worker hour works, it produces 10 units of output, right? So technically, it's bringing in $10 worth of output, right? Revenue, sorry, $10 worth of revenue, and it costs you $10. So you might be like, I don't know if I should employ this hour or not. Well, look at the next one. If you employ the next hour, that next hour costs you $10, but it's bringing you $12 worth of revenue because you made 12 units, it made 12 units, and each unit you can sell at $1. So it's profitable to employ that second hour. Let's think about the next hour. That next hour, the third hour, costs you $10, but it's bringing in at the margin 14 units of output. You can sell each of them for $1, so it's bringing in $14. It is profitable to employ this hour. And again, you might have thought, well, you should stop at 3 because it's the most productive unit. And I'm here to tell you, because if you stop at 3, you don't employ the 4th hour, you are leaving money on the table. This 4th hour is also worth it. It costs you $10, but it's bringing in $13 worth of value. It's called value marginal product. Okay, it's bringing in $13 worth of value. It makes 13 units. You sell it at $1 a pop. It's bringing in $13 worth of value. So employ the 4th hour? Absolutely. What about the 5th hour? Should you employ the 5th hour? Yeah, the 5th hour costs you $10, and it's bringing in 11 units. It's making 11 units times $1 a pop, so it's bringing in $11. The 5th hour is profitable. Employ it. Remember, principles of chapter 1. Rational decisions are made at the margin. At the margin, the 5th hour is profitable. Employ it. But the 6th hour, it only makes 7 units of output, which means you can bring in $7 with that hour. But it costs you $10 to employ it. Bad idea. So where would you stop? Stop at the 5th hour, right? Either stop at the point where marginal benefit equals marginal cost, and the marginal benefit of production is the marginal revenue, the additional revenue brought in from additional production, or at the last point at which it's still profitable. And in this case, it's at unit 5 of labor. Okay. All right, so again, don't fall into the trap of thinking, well, the 3rd hour is the most productive, so that's how many units of labor I should employ. No, if you do that, you are leaving money on the table. So that's just to show you that just because we have this benefits of specializations, this negative part of the marginal cost curve, that doesn't mean you actually want to produce there. In fact, we just showed that we want to produce at a point where we've actually already kicked into diminishing returns. All right, so I wanted to make sure you understood that concept. MindTap will give you lots of practice. If you find this material to be challenging, by the way, we haven't gotten into the more challenging stuff yet, but if you are finding this material to be challenging, or even if you're not, I highly, highly, highly recommend that you do the adaptive test practice questions, because it will throw a bunch of questions at you for which you'll have to do these calculations so that you can get used to what you're computing and understand what the plots should look like. Let's see. Okay, let's go to the slides again. So let's assume that Farmer Jack pays $1,000 per month for the land. So going back to the farming of wheat, harvesting of wheat example, and that each worker costs $2,000. So these are going to be our working assumptions. Okay? So $1,000 for the land, the 5 acres, remember, and then each worker costs $2,000 per month. So output was measured on a monthly basis. Okay? So let's look at what cost should be. So here we have the two pieces of information we had before. As you employed more and more workers, what output increased to. Okay, and so let's look at the cost of the land. No matter how many workers you employ, the cost of the land is a flat $1,000, right? So because this is our fixed input, we should only have to pay that fixed amount. But labor changes. It depends on how many units you're employing. If you're not employing any workers, you don't pay any labor costs. If you employ 1 worker, it's $2,000. If you employ 2, it's $2,000 each. 3, $2,000 each. We get $6,000. 4, 5. Okay. So if we get to total cost, it's basically, according to our story, just the cost of the land and the cost of the workers. So we're going to add these two costs up, the cost of land and the cost of the workers. Right? So total cost is, again, the sum of the fixed cost. Fixed cost is a cost that does not depend on how much you produce. Notice that no matter how much you produce, your fixed cost is the same. It should be the same. By definition, that input is fixed. It does not matter how many units you produce. You only have those 5 acres of land. Your fixed cost, your fixed input has a fixed cost. But your variable input is labor. And that does depend on how much you produce. The more you want to produce, the more laborers or workers you need to employ. The more workers you employ, the higher your variable cost, right? Your variable cost here happens to be labor. So total cost is going to be the sum of the fixed cost, which is the cost of land, plus the cost of the variable input, the variable cost. Okay? And so again, 1,000 plus 4,000, we get 5,000. 1,000 plus 6,000, we get 7,000. That should be pretty obvious. And so now, using this information, we're just taking the output column and the total cost column to find marginal cost. And this is the total cost function. When we plot this, this is the total cost function. 0, 1,000, there we are. 1,000, 3,000, there it is. 1,000 bushels, your total cost is $3,000. 2,400 bushels, your total cost is $7,000, right, for those 2,400 bushels. And so this is the total cost function. Remember what I told you just a while ago. The slope of any total is the marginal. Again, the slope of any total function is the marginal. So if this is our total cost function, and we look at the slope is marginal cost. The change in cost when we change the output, right? So if we produce more, go from here to here, that's change in output, the change in our cost. We go from 1,000, and our cost goes up from $1,000 to $3,000, right? So the slope of a total is the marginal. Notice what the slope's, what's happening to the slope. The slope is immediately picking up, right? In other words, the marginal cost curve is immediately picking up. There's no point at which where that slope is actually decreasing. Okay? And so if we were to find marginal cost, remember marginal cost is the additional cost from additional output, right? In this case it happens to be 1, but I told you earlier that delta, the bottom part, doesn't have to be 1. So that's why I wrote in my definition the additional output, because it could have been delta Q is, in fact, in our example, delta Q isn't 1, as you'll see in a bit. But look at this equation. Marginal cost, the change in total cost when we change output, right? The additional cost, the change in total cost, when you change output. So let's find that. Okay. Here we have again our column of output, or column of total cost. Marginal cost, the additional cost from the additional output. Change in total cost was $2,000 from 1,000 to 3,000. Change in output went from 0 to 1,000. So 2,000 divided by 1,000, we get $2. Then do it again. Delta total cost, change in total cost was 2,000. Output changed by 800, so 2,000 divided by 800 is 250. Do it again. 2,000, the change in total cost divided by the change in output. The change in output happens to be $6. So 600. 2,000 divided by 600 is 333. Do it again. 2,000 divided by 400, $5. Do it again. 2,000 divided by 200, $10. And you'll notice that marginal cost immediately started picking up, which is exactly what that slope of that total cost function showed us. Immediately the slope was getting steeper, which means the slope, being marginal cost, right, marginal cost should immediately start to pick up. So if we plot this, here it is again. Now this is just that information condensed here. Move to the left. If we plot this, here we go. Marginal cost is immediately picking up. There's no point at which it's dropping, right? There's no little Nike swish here. It's immediate. It kind of looks Nike swishes, but it's not, because Nike swish means it's actually going down. There is no part where it's going down. It's immediately picking up. So this is what the marginal cost curve looks like for this particular story. Okay. So make sure you're able to do these calculations. Okay. We are going back to the whiteboard because we're going to focus on additional properties of cost curves. So I'm going to reintroduce you to fixed costs and variable costs, and we're going to get into the nitty-gritty of some additional properties of those particular cost curves. And as I said before, this is where it gets a bit challenging for students. So far we've talked about the production function, and I linked that to marginal productivity, right? We said that the production function is the total product function, and that the slope of it, the slope of any total is the marginal. So we linked total product, also known as the production function, to marginal product. And then we linked marginal product to marginal cost. And then we got to know, hey, when does the marginal cost curve have a Nike swoosh? When does it not have a Nike swoosh? So marginal cost is our first cost curve we've been introduced to, and it took us a little while to get to it. Now I'm going to introduce you to additional cost curves and some of their properties. And so let's start off by talking about total cost. And we've actually already talked about this part in that previous Farmer Jack example. So total cost regardless of explicit, implicit. That stuff we already talked about. We already said explicit, there's a payment for it. Implicit, there isn't. Here, we're assuming all of those costs are in here. Okay, so when I say total cost, it's both explicit and implicit bundled in there. And there are costs that are fixed because you have a fixed input, like the land or the building. I like to think of the building as being fixed because that's usually what is fixed, right? And that does not, the cost of that does not change with how much you produce. Whether you make one pair of shoes or 100 pair of shoes, the rent is still the rent on the building. Okay? And so that type of cost is what we call a fixed cost. And many of you are familiar with this from your accounting classes. And so again, fixed costs do not depend on output. And my tablet froze up. Hello. There we go. Do not depend on output. Doesn't matter how much you produce, whether you produce nothing or you produce 100 pair of shoes or 1,000, your rent is still your rent. Even if you produce nothing, you still have to pay your rent, right? So fixed cost is fixed. No duh. And then there are costs that do depend on how much you produce. We call those variable costs. They vary with output. Right? They depend on output. Vary, or in other words, depend on output. All right, vary with or depend, maybe I shouldn't say that. I should say varies with output or depends on output. If you don't make any shoes, you don't have to hire workers. In other words, you don't need to incur variable costs. Let's say you're running a restaurant and you've signed a lease on the building. Whether or not you make a hamburger, you still have to pay that rent, like we said. But you don't have to make hamburgers. You don't have to employ a worker. You don't need to buy tomatoes. You don't have to do that. No one's putting a gun to your head to do that. You do have to pay your rent because you signed a lease, right? You do have to do that, or maybe you have a mortgage out. You do have to make that payment. But variable costs are a choice. You can choose whether or not to employ more workers. Okay, so it depends on your output. If you want to make a lot of burgers, you're going to need a lot more tomatoes. You're going to need a lot more buns. These are variable inputs. You're going to need more workers the more people you want to serve. Okay. All right, so total cost is equal to the sum of fixed costs plus variable costs. And we're actually going to just use abbreviations here. We're going to say total cost is equal to fixed costs plus variable costs. And if we wanted to find the average cost of production, on average, right? What's your average cost of making a meal or making a pair of shoes? What would you do? You would divide your total costs by how many units you're producing, right? So that would be your average total cost. Well, whenever you do that to the left, since total cost is made up of fixed costs and variable costs, then that means you have to do it to the right as well. So, what's this telling us? This is telling us that the average total cost is the sum of average fixed costs, on average, what's your fixed cost, plus, on average, what's your variable cost, right? And so we're going to use abbreviations for that as well. We have average total costs. Let me write it out, actually. Is equal to average fixed costs, bear with me, plus average variable costs. Average total cost is the sum of average fixed costs plus average variable costs. And how did we get that? We just divided by Q here, right, which took us to this equation, and then we just wrote out what that means. And so now we're going to use abbreviations for this. This is ATC, your average total cost of production. This is AFC, your average fixed cost of production. On average, what's your fixed cost per unit? And then your average variable cost. On average, for the average unit, what's your variable cost? Okay. So we're going to focus on this representation of it. Average total cost is the sum of average fixed costs plus average variable costs. And so these are 3 additional cost curves that I'm introducing you to. Technically, I've introduced you to total cost. First of all, we already talked about marginal cost. Here's total cost. Now you know fixed cost. Now you know variable costs. And now we're adding average total cost, average fixed cost, and average variable cost. Right? Don't confuse average variable cost with variable costs. They're different. One is the total variable cost, the top one, and one is the average variable cost. Okay, so this is what I'm going to focus on, understanding the properties of these cost curves. I believe there are 5 that we're going to focus on, and I'm going to write them down here. I'm going to list them. And I don't think they're listed the way I list them here in the textbook. I don't think they're listed that way in the book. But I like to list them here so that you know, hey, I need to make sure I master these properties and I understand why these curves look the way that they do. Not just be able to draw them, but understand why are they related this way. What is the economic intuition behind these concepts? And so let me list them. So it's going to be properties of the average cost curves. In other words, ATC, AFC, and AVC. And there's 5 of them. 1, in no particular order, but I happen to like to go in this order. Average fixed costs is decreasing. Whoops, that's not how you spell decreasing. Average fixed cost is decreasing in quantity. So average fixed cost is decreasing in quantity. And let's look at what that means. First of all, let's write out what average fixed cost is. Nope, that's wrong. Again, not a mistake, a teachable moment. Average fixed cost is not AFC divided by Q. Average fixed cost is FC divided by Q. That's what average fixed cost is. Right? Average fixed cost is fixed cost divided by quantity. And remember, fixed costs are fixed. So if you want to put a little bar here to remind you of that, you can. It does not matter how much you produce. Your rent is your rent. It's the same whether you make 1 burger, no burgers, or 29 burgers. Your rent is still the same, or the mortgage payment is still the same. So as you produce more, that fixed cost is fixed. So if the denominator is getting bigger, that means you're spreading that fixed cost across more units so that on average, fixed costs are going down. Right? You're dividing by a larger Q, you're spreading that fixed cost across more units, average fixed cost is decreasing. And that's exactly what this statement says. Average fixed cost is decreasing in quantity. Meaning as quantity is increasing, average fixed cost is going down. So you should be able to plot this. Right? We're going to plot $ here because it's the cost of production. Right, the cost of production. So $, and then what should it look like? It should look like this. As, this is again average fixed cost. As you produce more, technically I guess I should use a big Q since I've been using a big Q all along. Right now it doesn't matter. You can use big Q, little q, doesn't matter. Chapter 14, it will matter if you use big Q or little q. Right now just think it's the quantity of output. As you produce more, you're spreading that fixed cost across more units, so your average fixed cost is dropping. Right? So as you produce more, average fixed cost is going down. In other words, we're going in that direction. Right? So this is what the average fixed cost curve looks like. It will never touch the x-axis. It will asymptote towards it. It'll get really, really close to it, but technically it'll never touch it. Okay? And average fixed cost curve will always look like this. It is decreasing in quantity. So that's one property. All right, on to the rest. Remember, we have a total of 5. And let's see. So the second one, actually the second, the third, and the fourth go together. The fourth one is going to be a pill that I'm going to have you swallow. Why? Because I'm your professor and I said so, but not for long. Okay, and I'll get back to that in a second. So second one is, so let's see, ATC is, I'm going to emphasize graphically, ATC is above AVC. That should make sense, right? That ATC is above AVC, especially also graphically. Why? Because we know that average total cost is equal to average fixed cost plus average variable cost. So of course average total cost is going to be above AVC, assuming fixed cost exists. If fixed costs are zero, then they're technically the same curve, right? If fixed costs are zero. But we're going to assume that fixed costs are non-zero, especially because we're in the short run. In the long run, there are no fixed inputs, meaning there's no fixed cost. So in the long run, there's only one curve, ATC. ATC is AVC. Okay, but these are properties, by the way, of the short run. Okay, so we're going to assume that there is a fixed cost. And so ATC is above AVC? Yeah, no duh, Professor Malice. Of course it is. Okay, so number 2, I'm not going to draw it yet. I'm going to list numbers 3 and 4, and then I'll draw it. Number 3, let me think. Number 3, here we go. ATC, average total cost, and average variable cost converge in quantity. So anytime I say in quantity, it's this, right? As quantity goes up, that's what I mean by in quantity. Average fixed cost is decreasing in quantity. As quantity goes up, average fixed cost goes down. So ATC and AVC converge in quantity. So that's the third one. Let's layer on the fourth one, and then we'll combine all 3 and draw them. So the fourth one is a pill that I'm going to have you swallow. In other words, just do this and believe me because I said so. Just trust me, in other words. But I promise you that I will explain what it means and why it is the case. Everything in this class will always be explained to you. You should know that by now. Everything makes sense. It does require some work to understand a lot of it, but it all makes sense. And I'm never, ever, ever going to leave you hanging in terms of, oh, here's some, I'm waving my hands and here's some magic and you know, just believe me because I said so. Yeah, maybe initially, but I will always explain it. Why? Because that's my goal. My goal is to have this make sense and for you to understand these things, and also because I'm going to test you on them. Okay, there's no bullshit in this class, none whatsoever. You should know that about me already. You should know that about economics already. Okay, all right, so ATC is graphically above AVC. ATC and AVC converge in quantity. And then the fourth one is ATC. I'm thinking. I don't have any notes. If you knew me or if you've ever sat through one of my classes, you know that I don't use any notes. I'm just thinking about what I need to teach you. And that's why it takes me a little while sometimes. ATC and, oh goodness, I forgot now. ATC and AVC are U-shaped. So this is the pill. U-shaped, meaning like U's. Right, kind of like a happy face. Why? Because I said so, for now. Okay, just give me a bit, and in a little while you'll understand why they're U-shaped. But for now, just swallow the pill, draw them like U's. So let's combine these 3 together. Oh, I think you might have heard my kitty right now. All right, so the costs of production. The costs of production, chapter 13. Here we go. I'm going to zoom in on this. So first of all, ATC needs to be above AVC. We know that. They need to come closer as we produce more. They need to converge. And they need to be U-shaped. So here we go. There's ATC, average total cost. It is above average variable cost. Average variable cost is also U-shaped, and they come together as quantity increases. So here's my U-shaped AVC. Not only is it U-shaped, but as quantity increases, the gap between them is smaller because they're converging. That's what we mean by number 3. So notice that we have all 3 properties here. ATC is graphically above AVC. ATC and AVC converge as quantity increases. In other words, they converge in quantity. And fourth, ATC and AVC are U-shaped. So let's make sure we understand. We already understand why ATC is above AVC. We know that because ATC is average fixed cost plus average variable cost. And why they converge is also because of that. Because the gap between them, it is average fixed cost. That's the gap. That's the difference. Right? It is. For this particular unit, here's the average variable cost. Add to it the average fixed cost. You get to average total cost. So the gap between these 2 U-shaped curves is average fixed cost. And notice that the gap, as we produce more, that gap is getting smaller. as it should be. Why? Because the gap is average fixed cost, and according to number 1, which makes a whole lot of sense, average fixed cost is decreasing in quantity, because as we produce more, we're spreading that fixed cost across more units. Therefore, average fixed cost has to go down as we produce more. The gap is average fixed cost, so it better be that the gap is getting smaller in quantity as we produce more. So that explains number 3. ATC and AVC converge. They come together in quantity. Why? Once again, because of number 1. Okay, again, these cost curves are related to each other. Now, number 4, why are they U-shaped? It's because I said so, right? Well, let's get into that. Why is that the case? And to understand that, we need to add number 5. Marginal cost. It's back. Marginal cost intersects, meaning it slices. It intersects average total cost and average variable cost at their minimum points. So marginal cost intersects average total cost and average variable cost at their minimum. Let me draw that. So number 4 is the case because of number 5. And so, again, the cost of production. And let's draw our curves the way they're supposed to be drawn. Average total cost is U-shaped, and it's graphically above average variable cost, which is converging towards it. And marginal cost intersects them at their minimum. This looks like it's the minimum of average variable cost, so I'll write AVC min. And let's see if I can find the minimum point here. It's kind of there. Maybe not exactly drawn properly, but who cares? I think we all agree it's basically there. And now I'm going to carefully draw my marginal cost curve. Remember, marginal cost can be, like that. So marginal cost can immediately pick up, which means marginal productivity immediately started to diminish. Or it can be, can have the little Nike swoosh. I happen to like the Nike swoosh. And again, we understand when we have the Nike swoosh, when we have the benefits of specialization, that's when marginal cost goes down, which means marginal productivity is going up, right? This should all link. So I'm going to draw this one because I like that one. And so let's make sure we superimpose that here with making sure that this condition holds. Marginal cost intersects average total cost and average variable cost at their minimum, right? So I'm going to be careful when I draw it. Again, there I have my U-shaped kind of average variable cost curve and average total cost curve, right? And so I'm going to be careful. Kind of goes, oh, I did it. Whoa, yay. Sometimes I have to erase it. So there's my marginal cost curve, right? Intersecting both of these curves at their minimum. Notice that all of these properties hold. Average total cost is above average variable cost. Their average total cost and average variable costs are converging in quantity. The gap between them is getting smaller. Also notice, by the way, that I'm not superimposing average fixed cost here. Why? Think about why I'm not doing that. I don't need to do that because this information that average fixed cost is decreasing in quantity is already in the gap. It's already implied in the gap. So that's why I'm not layering an additional cost curve here. In the slides, it is in there, and I think in the book maybe. But eventually, if you keep on going through the slides, I get rid of that. Why? Because why put it in here if it's already implied? Whoa, I erased too much. If it's already implied, oh, hello. If it's already implied in the gap, right? So why add it in? That's why I exclude it. Anyway, marginal cost intersects average total cost curve and the average variable cost curve at their minimum. Why? To understand that, let's focus on one of them. I'm just going to focus on the average total cost and marginal cost. I'm going to get rid of average variable cost just to get a point across. Okay, so let me redraw this. And I'll erase this. The cost of producing, Q, quantity. And so we have our U-shaped average total cost curve. And marginal cost is slicing it at its minimum. Perfect. Okay. And this point here, I'm just going to call it Q naught. Notice that that's the quantity, that marginal unit, that Q naught unit, that one there. Not these, not the total, that one, that marginal unit. For that marginal unit, marginal cost is equal to average total cost. That's where the two curves intersect. Okay. But anywhere to the left of it, let's say this unit red, that red unit, that marginal unit. Marginal cost is lower than average total cost. Think about what that means. You've made this many units up until that marginal one. And let's say on average it's costed you $20 to make those units on average. You decide to make this marginal unit, not these, but that one. You decide to make that marginal unit right there. And on average it's costed you 20 bucks, but the marginal one costs you $8 to make. That next one costs you $8 to make. What happens to your average? Your average cost goes down. You're pulling your average down, right? You're pulling it down. Why? Because at the margin, it's cheaper to produce that next marginal unit than it's costed you on average, right? So it pulls your average cost down. To the left of Q naught, it is the case that marginal cost is less than average total cost. It costs you $8. It's been costing you $20. Of course you're going to pull the average cost down because the next unit you produce is cheaper than it's been costing you. So it pulls that average total cost curve down. If you are to the right, somewhere over here, think of this blue marginal unit, the 102nd unit, let's pretend. For that one, the average cost is here. And at the margin, it costs you more to make it than it's been costing you. Let's say it's been costing you on average $17. And this next marginal one, the blue unit there, that one, costs you $25 to make. On average, it's cost you 17 so far. Then you make this one, it costs you 25 at the margin. What are you doing to your average? Your average cost goes up. Why? Because at the margin, it's costing you more than it's been costing you on average. So of course you're going to pull your average cost curve up. What happens to the average is determined at the margin. If marginal is above average, it's going to pull the average up. We're over here on this side. If marginal is below the average, it's going to pull the average down because at the margin it was cheaper to produce than it's been costing you on average. And if you're at this unit, it costs you on average 15 bucks to produce, and the next unit you make is $15. That's your marginal cost. And what happens to your average? It stays the same. Right? So that's where they intersect. Once again, what happens to your average is determined at the margin. That's a super important principle, folks. It'll apply to so many things in life. I think that's a pretty useful principle to walk away with just in this class, just to be like a regular person out there, or actually a better informed person. What happens to the average is determined at the margin. I'll give you a few examples. One, I just gave you this cost one. Here's another one. Suppose we're all in a classroom together in our physical classroom. We're physically there. And let's say we take the average height of all of us here. Maybe one student is missing. And we take our average height, and our average height is 5'8". And along comes the student who's missing. He or she is late. And that student happens to be, that's the marginal student, by the way. Marginal student walking in. That student happens to be 6'4". At the margin, greater than on average, what's going to happen to our average when this person walks in? It's going to pull our average up. We're on the right-hand side. We're over here. Right? Close your eyes. If our average height, now change the story. If our average height in our room is 5'8", and then along comes a student late who happens to be 5'3", what is that going to do to our average? The marginal's 5'3", our average has been 5'8". It's going to pull our average down because the marginal's below the average. Once again, what happens to the average is determined at the margin. Here's another example. I'm an economist. I'm also a person. And if you know me, I've got these curvy hips. I'm a Latina. I can't help it. For the most part, my jeans, I look at food and it like attaches to my thighs. And here I am teaching you that what happens to the average is determined at the margin, that fucking margin, I swear, man. Because, again, the hips are determined at the margin, right? So I struggle at the margin. Not so much to, it's also a lot of it is genetic, Latina. But again, how heavy that not heavy as in weight, but heavy of a weight on the margin is influenced by genes, but still, at the margin, again, the average is determined at the margin. So that's an example. Here's another example, and this is one that definitely applies to you. Your GPA, your overall GPA, right? Your overall GPA prior to the semester, walking into the semester, it is what it is. That's your overall GPA. That's your average GPA walking into the semester. Right now, we live at the margin, ladies and gentlemen. You are in the margin. The only way you are at the margin. The only way to improve your overall GPA is if at the margin you do better than you've done on average so far. So if you have a 3.0 and this semester you get a 3.2, you're going to pick that average up, your overall GPA. But if you get a 2.9, honey, you're going to pull it down. The only way to improve your overall GPA is to do better at the margin, right? So again, the average is determined at the margin. So now we understand all 5 of these properties, right? Let's go back and kind of recap them rather quickly. Number 1, average fixed cost is decreasing in quantity. Number 2, 3, and 4, they go together. ATC is above AVC. That one's easy. ATC and AVC converge because of number 1, average fixed cost is decreasing in quantity. And they're U-shaped, ATC and AVC. Why? Because of its relationship with number 5. Marginal cost intersects them at their minimum, right? And I happen to focus on average total cost when I did this, but I could have just as easily replaced this T with the V and looked at average variable cost. The same concepts hold. All right. Now, by the way, these are all short run properties especially because we've been saying that fixed cost exists. In other words, there's a gap. Okay. We are now going to move into the long run and we're going to talk about what is known as economies of scale. To do that, we're going to go to the slides. So economies of scale. Remember in the beginning, I told you to think of the word scale as in size. Economies of size, changing the size of the firm. And to change the size of the firm, that means you're changing all of your inputs. You're doubling all your inputs if you're doubling the size of the firm. You're tripling or you're halving them. So a scaling concept has to be a long run concept because that's the only way you can change all of your inputs if by definition you're in the long run. Again, because the long run is the period in which you've kicked into all inputs being variable. Nothing is fixed. You're out of that lease obligation. You're out of that mortgage. You can change the building. You can get into a bigger building, a smaller building, buy more machines, buy fewer machines, whatever. Okay. And so we're going to assume that we have 3 choices for the size of the firm. The firm can be small, or the firm can be medium, or the firm can be large. By the way, we're describing long run, LR, average total cost. Okay, with 3 different factory sizes. And so again, assuming there's only 3 different sizes, totally unrealistic. In reality, there's a bunch of different sizes a firm could be, but let's just assume 3. So we're going to look at costs of production, particularly average total cost. Again, in the long run, we're going to build the long run curve, and you're going to see that the long run average total cost curve comes from the short run. So 3 different sizes. By small, I don't mean small square footage of the building. I mean small as in small level of output, what we call the relevant range. The relevant range is in this lower part, or medium would be somewhere here and large would be somewhere here. The relevant range, meaning the applicable size. Okay, and so each size, if you're small, if you're servicing a small amount of output, not small as in 1, 2, small relative to the whole market, okay, or to how much you can produce. Not the whole market, how much you can produce, the individual firm. And so if you're chosen to be small, then you've chosen to produce here, meaning you've chosen the size of the firm, the building, the amount of labor that you need, the amount of machines. So you're in the short run if you've made a choice to be a particular size. If you have made a choice, you are in the short run. If you can make a choice to change the size, you are in the long run. Okay. But where do we live? We actually live in the short run. In the long, we don't live in the long run for long. Because think about it. If a firm's lease is up, what do? Boom, they renew the lease. Or boom, they change buildings. Or boom, they shut down. Or boom, something. They don't stay in the long run for long. They rather quickly jump right back into a new short run. Just like relationships. Right? You're with someone, you're in the short run, you're kind of pinned down, you're there, you're not leaving until, I don't know, maybe the lease is up, or maybe until you get out of school because he or she's helping you pay, and you think it's funny or not. You're like, she's sick and twisted again, damn economists. But it's true for a lot of people. People stay in relationships because of cost, right? Sometimes it does influence relationships. And I'm not saying that's a good reason to do it, but does it? Yeah, it does. Right? And I'm not saying you should leave. Maybe you should stick in this short run. Maybe this works. Stick there. Maybe this is optimal for you. Okay, fine, stay there. Right? Don't jump into, another. If you have a choice to make again, maybe there's a big fight, and then you come to terms and you choose to stay. Okay, you were temporarily in the long run, then boom, you chose to stay, both of you. Okay, you've chosen to be in the short run again. Okay. Anyway, so cost curves linking production to relationships, they're applicable. Like I told you, economics of the household, it's a real thing. Anyway, so if you've made a choice, you're in the short run. If you have a choice to make, you are in the long run. All right, so if you've decided to be a small firm, then your average total cost curve would be here, and you can only basically service this many units. Okay. And if you've chosen to be medium, your average total cost curve, again, these are short run curves. This S does not stand for short run. This S stands for small. So if you want to add an S and an R right here, SRATC, you can for short run average total cost. That's what these are. Short run small, short run medium. And if you choose to be large in the short run, then this is the average total cost curve to be large because you're servicing these higher quantities up here. Okay, so now that we know this, let's ask what would be the optimal size to be? If you had a choice, meaning if you're in the long run, where would you choose to be? What size? Given how many units are optimal for you to produce. We haven't talked about how you choose the optimal quantity. But we're going to talk about, suppose your optimal quantity is in this range, or suppose your optimal quantity is in this range. We're going to ask, what size should the firm be in the long run? So let's do that. Let's split it up into these two ranges, where they intersect here, the small and the medium, and where the large and the medium intersect here. Suppose your optimal quantity of shoes or of wheat to produce, which we haven't identified how to choose the optimal. That's next chapter and the chapter after that. But for now, suppose that the optimal quantity for you to produce is between here and here. What size would you want to be in the long run? Would you want to be medium? Can you be medium? Sure you can. If you want to service this many, sure you can be medium. There would be your average total cost. But do you want to be there in the long run? No. In the long run, you'd rather be small. But in the short run, maybe you're medium and you're stuck because you signed a lease and you realize, oh crap, as soon as I get out of that lease, I need to turn into a smaller firm. Right? Why? Because it's optimal for you because it lowers your average total costs. Right? So if you're between here and here, you would want to be a small firm, but you might be medium in the short run, but as soon as you get a choice, you'd want to stop being medium and then go be small. Can you be large? Oh yeah, imagine this curve goes up all the way up here, your average total cost curve for the L, large. Sure, you can be large, but that's a really bad idea. You're going to actively try to get out of your short run, actively try to get out of that lease, right, so that you can then come and shrink the size of the firm, for example. Okay, so if you're between here and here, you'd want to be small. What about if your optimal output is to produce between QA and QB? Can you do it as a small firm? Sure you can, but that's not optimal. You might be there in the short run, but in the long run, as soon as you have a choice, you're like, boom, I need to be a medium firm. Can you do it as a large firm? Yeah, pull that curve all the way up there like a parabola. Sure, you can do it. You can produce this many as a large firm. Your average cost is way up here. If you're there in the short run, you're going to be like, I need to get out of my short run and choose to be medium. As soon as I can change the size of my firm, I'm going to be medium. So again, anywhere between QA and QB, what's optimal for the firm would be to be a medium-sized firm. Now to the right of QB, the optimal size in the long run would be to be a large firm, because you can do it as a medium firm, but your average cost would be higher than if you were a large firm. So it would be optimal to be large. You can probably also do it as a small firm, but that goes like way up here, right? Even higher than this. I can't go any higher on my screen. But so you'd want to not be a small firm. As soon as you get a chance, you're going to switch to scaling up, being a larger firm. Remember, scaling is a long run phenomena. So what is optimal depends on what your relevant range is. Is your relevant range here? In which case, in the long run, you'd want to be small. In the short run, maybe you are small. Great. You're where you should be. Maybe you're medium. Oh, get out of that. Maybe you're large. Get out of it. Right? You'd want to be small. If you're here, if this is your relevant range, what is optimal for you to produce, optimal that achieves your objective, remember the objective is profit maximization, then you'd want to be medium. And if it's over here, then you'd want to be large. And so what we're going to do is we're going to say, okay, let's choose the collection of optimal points. If these were the quantities we wanted to produce, let's hug these curves and choose what would be optimal for us. Right? So let's do that here. We would hug the optimal sizes given these different quantities. If we're between here and here, if it's here, this is the optimal size, small, and here'd be my average cost. If this is my optimal quantity, then I'd be small, and here's my average cost. If this is my optimal quantity, then I'd be small, and here's my average cost. If this is my optimal quantity, I'd be medium, and here's my average total cost. If this is my optimal quantity to produce, I'd be medium, and this is my average total cost. So what are we doing is we're hugging these cost curves at their optimal levels, right? We're hugging them. This is known, by the way, as the envelope theorem. You don't need to remember that for this class, but I know a lot of you either come from a math background or are going into math or are taking more econ, and you're going to hear this concept a lot, the envelope theorem, even in classes outside of economics. And I took a whole lot of math, and it took me so long to figure out what the envelope theorem was doing. I knew how to do it. I would do it because I learned mechanics. But it took me a while, not because I was dumb, but because no one really pointed it out to me, and it was all new to me, right? And so I'm going to do you a favor and tell you what the envelope theorem is. The envelope theorem is the collection of optimal points. That's what it is. We're hugging these curves at our optimal points. Where would we be our optimal sizes, and what would be the corresponding average total cost at these optimal different sizes? Right? So the envelope theorem is hugging them, and it's the collection of optimal points. Okay. And so if we remove the short run curves, actually let me back up. Actually, no, let's go ahead and do this. Let's pretend now that it's a more realistic situation in which you have a bunch of different sizes of the firms. It's not just small, medium, and large. It's really smaller, a little bit bigger, 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 and even bigger, right? So it's really a lot of different sizes that we can be. And if we wanted to produce this many, then we'd want to be whatever size corresponds to this, and there's where our average total cost would be. If we wanted to produce this many, then we'd want to be whatever size corresponds to this average total cost curve in the short run, and there would be our average total cost. So now doing the same thing that we did before, hugging the collection of optimal points, in other words, enveloping the short run to get the optimal sizes in the long run, we get this as our long run average total cost curve, the collection of optimal points rendering our long run average total cost curve. And this now is what the long run average total cost curve looks like. Again, it's the collection of optimal points given the sizes that are optimal for us given how much we want to produce. So this is what the long run average total cost curve looks like. And so it is still U-shaped, but notice that it's got this downward point, a flattish part, a flat part, and then it picks up. Okay, let's go to the whiteboard to understand some properties here, and then we'll finish up. Okay, so still on the concept of economies of scale. Again, economies, saving by scaling. Or potentially dis-saving. It could be diseconomies of scale. So we've built already the long run average total cost curve. Let me redraw it here. Again, the costs of production, chapter 13. And so our long run average total cost curve has this negatively sloped part, this flatter part, and then it starts to pick up. That's a terrible plot. Let me do it a little bit faster. There we go. And so this is the long run average total cost curve. Again, it's made up of all of these short run ones, right? But I'm going to erase them. And this is supposed to be kind of flattish. I think it's pretty flat there. Okay. And let's split it up into ranges. this is going down on the left-hand side of it. Then we got the flat part. Then it starts to pick up. Okay, we'll call this region 1, region 2, or maybe let's use letters since we just finished using numbers. We'll call it region X, region Y, and region Z. Okay, and so let's talk about what's happening at region X. Okay. Notice that if we're in region X, as we produce more, we're dropping average total cost. Average total cost is going down, long run average total cost. This particular region is what is known as economies of scale. Actually, I'll write it here. Economies of scale. In other words, savings by scaling, by getting bigger. And let's understand why that's the case. So under region X, okay, notice what's happening. Average total cost is dropping as we produce more. When this is the case, we have a concept known as increasing returns to scale. Also known as IRS, increasing returns to scale. So in this region here, we have the production function is exhibiting increasing returns to scale. In other words, the average total cost curve is going down as we scale up, as we get bigger. We produce more, right? We get bigger in terms of the size of the firm. And look at what this means. Let's look at the average total cost curve. Actually, let me write some things. If we have increasing returns to scale, first of all, let's understand what this means. The returns to scaling, what are the returns to production? It's the output, right? The returns that you get from doing what you do is whatever you produce. Those are the returns. So the returns from changing the size of the firm are increasing, meaning as you get bigger, let's say you double. Let's say you double the inputs. So let's say doubling inputs, that's the scaling. That's the scale part. You doubled all your inputs, long run, all of them. That leads to a more than doubling of output. Doubling inputs more than doubles output. You scaled, you doubled inputs. The returns were more than doubled. They were increasing. It was proportionally greater than the size of your scaling. Increasing returns. You doubled inputs, you more than doubled output. Look at what that does to your average total costs. Average total costs is what? Total cost divided by quantity. If you doubled inputs, let's assume that cost of every input stayed the same. The cost of labor, the cost of wood, of plastic. Let's say that stayed the same per unit. So if you doubled your inputs, twice as much labor, twice as much wood, twice as much plastic, then that means you doubled your total cost. Again, doubling your inputs doubles your total cost. But your output more than doubled. Let's say it tripled. It used to be Q, now it's 3Q. You doubled your inputs, which doubled your cost, but your output more than doubled. It went from Q to 3Q. What did you do to your average total cost? You brought it down. Average total cost is lower. And that's exactly what's happening here. As you get bigger, your average total cost is coming down. Why? Because you must be exhibiting increasing returns to scale. If you're a producer, do you like this property? Hell yeah, you do. In fact, this is the only IRS that firms like. Increasing returns to scale. They love operating under increasing returns to scale. Why? Because it's bringing their average cost of production down in the long run. So that's increasing returns to scale. Now let's look at region Y. And to do that, I'm just going to erase this so that we keep everything on the same screen. Region Y. So at Y. Region Y. This is what we call constant returns to scale. also known as CRS. Constant returns to scale. It's in the title. The definition is in the title. Constant returns to scale. So we scale. We doubled inputs. The returns to scaling, meaning the output, was constant, meaning it was proportional. So we doubled inputs. What do you think it does to output? It doubles. Constant returns to scale. We doubled inputs, that doubled output. Okay, let's go back to our average total cost function. If we doubled inputs, that doubles our total costs. And by assumption, our output doubled. So what happened to average total costs? Nothing. It stayed the same, and that's exactly what's happening here. As you produced more, as you scaled up, your average total cost stayed the same. There's that flat part. Right? So that's constant returns to scale. Now the last part. What do you think it's called? As we produce more, we start picking up the average total cost. It's not increasing returns. It must be decreasing returns. DRS, decreasing returns to scale. As we produce more, we start picking up our average total cost of production. So this is what at Z, we call this decreasing returns to scale. It's in the title, folks. The definition is in the title. Decreasing returns to scale, also known as DRS. And so we're scaling. Here we go. I happen to choose doubling, but it could have been tripling. Doubling inputs, the returns less than double. They're decreasing returns. So doubling inputs, less than doubles output. Decreasing returns to scale. So let's go to our average total cost function. There we go. We doubled inputs, which means our total cost doubles. But our output less than doubled. Let's say it goes to, I don't know, 3/4. It less than doubled. Actually, it doesn't even have to be that small. It could be 4/3. Right? Because 4/3 is 1 1/3. So output increased, but it less than doubled. Right? So we know that when we divide by a fraction, it's the same thing as multiplying by the reciprocal. Right? And the reciprocal of 4/3 is 3/4. Well, what does that turn into? We get these canceled out. That turns into a 2. This is a 1. We get what? 3/2. And so our cost turns into 3/2 of what it used to be. In other words, 1.5 times of what it was originally. When we doubled inputs, our costs increase. Right? They're now on average 1.5 times bigger than they were before. Right? So this should make sense. Right? This should make sense that average total cost is picked up. We doubled inputs. There we go. We're scaling. We have picked up our average total cost of production. This is not what we call economies of scale. We call this region, which is exhibiting decreasing returns to scale, we call it diseconomies of scale. We've gotten so big that we've kicked into diseconomies of scale. This does happen to firms. Why? One of the main reasons is because of the network gets so big. Think about it. You get so big, you have to start incurring a lot more costs, right? Before you had a manager, one manager, two managers that can handle a few, you know, assembly plants or whatever, a few retail outlets, whatever it is that you're doing. And then now you've gotten so big that you're starting to lose track. You need to hire a lot more people to just manage it. So that's one of the main drivers of it. I don't need you to worry about that, the why so much. I just want you to understand this concept of increasing, constant, and decreasing returns to scale, and how scaling, what it's doing to the returns, and therefore the impact that it has on average total costs. Again, this is economies of scale, the concept, but we should really put in parentheses diseconomies. By the way, this one here, between here and here, this one has no title. We just have a title for this region, that region, and this one we just say, well, it exhibits constant returns to scale. Super dirty, super sloppy, super messy, I should say, but fundamentally explaining why the long run average total cost curve looks the way that it does and the properties that it exhibits on these different regions. This is the hardest part, I think, of the chapter, but again, those characteristics also matter, understanding marginal productivity and linking it to marginal cost. What is marginal product? What is marginal cost? Being able to compute these things, being able to work through those tables on the slides, in the textbook, in MindTap, in adaptive test prep. It's important. So make sure you practice this a lot, folks, because this stuff, if you get it, it's easy. You compute it, you crunch it because you put in the time. It shouldn't be something that holds you up on the exam, but it does require quite a bit of time as usual. Okay. All right, folks, that's it for chapter 13.